Okay, so let us start the class today. So the basic idea that I want to capture is the following. As I mentioned, I want to cover now something about demographic noise.
Sir, will we also have the lab session today?
Will I have a lab session? It depends. Yeah, it depends on how much I'm able to cover. Huh?
Okay.
Okay. Uh, okay, so I want to cover how do we construct demographic noise from first principles, okay? From first principles. So first of all, what exactly is demographic noise? Demographic noise is usually a term used in the context of population dynamics. As we know, the birth process, and that of death, they're all stochastic, right? And we learned one model of birth and death in advance. The contact process, the spatially explicit model. And but when we wrote down the mean field model, the mean field model was deterministic. Okay. Now technically this is correct only in certain limits. Okay. And one such limit is the fact that the population size, must go to infinity for the mean field approximation to hold true. This is not sufficient, but this is necessary. Okay. Condition for the deterministic approximation to hold. Okay. The other conditions being, the spatial dimensions also matter. How accurate the predictions of mean field approximation depends on the spatial dimension also. There, it actually usually improves with increasing dimensionality. For example, if we had a one-dimensional system, the mean field approximation is not so great. It even can get the, whether the transition is continuous or discontinuous wrong. Second, two dimensions, it's better. Again, it can still be wrong. It will be surely wrong numerically, quantitatively. And three dimension, the approximation improves. And, in physics contexts, it turns out that the mean field approximation is accurate in quantifying various properties of the transition in fourth dimension, of course, which is not really the real world anymore. Okay. But nevertheless, mean field approximation are very, very useful. Okay. So, but when we say typically mean field approximation, we often mean deterministic approximations, but it's also sort of possible to capture the stochasticity. Okay. Now, when this n is not infinitely large, n is finite. When n is finite, the variation around the mean becomes important, right? And therefore, we cannot fully ignore variation. So therefore, we expect that the dynamics must also be able to capture something about the variation. Okay, so typically that sort of classic way of incorporating demographic noise, which is heuristic, which is not really a derived one, is as follows. If the mean field approximation looks like this is the mean field approximation. What people do is they basically say that, argue that, as the, the density changes, the strength of the noise changes. So this is a standard way of incorporating demographic noise for demographic noise. Just using heuristics. The idea is that the strength of the noise here is proportional to the density itself. Okay. When I say strength of the noise, I actually mean variance here. Okay. So very small density should have small fluctuations, because imagine the scenario when rho is going close to zero, right? You don't want the stochasticity to push you back to the negative terms. Okay, so the stochastic strength also must go down. Therefore, the strength of stochasticity must be proportional to rho, and this is the simplest approximation one can make. And as the density increases, proportionality of fluctuations will also increase. That's a broad idea. Okay, it's a heuristic though. It's not really derived from many principles, any mathematical derivation, but it is actually possible to do so. Okay, so today I'm going to introduce a method called chemical Langevin approach. Okay, that helps us construct what exactly is this term given a set of interactions. For example, you remember that we studied contact process, right? Where we said that 1 0 with some probability p becomes 1 1, and then 1 with some probability 1 minus p becomes 0, right? There is stochasticity here. Now, how does this stochasticity in this actually translate to this multiplicative noise? Okay, that this approach called chemical Langevin approach will help us. And also remember another model we studied, which is the binary choice model, where we said that x1 plus x2, right, can become 2x1, right, or 2x2. Where you copy the choice of the, one of the randomly chosen numbers. Simultaneously, individuals can also change their decisions spontaneously with different rates, C and S. Okay, so in these cases, we have learned how to write down the mean field model. The question is, how do we now try to? How can we learn? How can we learn to write the multiplicative, noise term? Okay, so let's see. So this might be slightly technical. I will give you a reference to read later on. A paper by Gillespie, 1970s, 80s. And one of my students also wrote a review article that nicely summarizes it. So I can also share that with you. Okay, now the basic idea, you need to know a few terms that I am going to use now. So a few terms. So the method is called chemical Langevin equation. I'm not going to derive it. I'm just going to sort of intuitively argue why it will look like this. Okay, and it's closely related to the mean field approximation. It's not like fundamentally different. Okay, so you need to know a few terms which I will define. Those terms are, first one is something called propensity function. Okay. And the second one is called basically what we call state change vectors or matrices. Okay, so let us try to understand what these terms mean. Okay, so let's again take a very simple example we already have. It helps to sort of take the example instead of doing it very generally. So let's take the simple binary choice model as the example. Remember that we had these simple rules. X1 becomes X2 with some rate f. X2 becomes X1 at some rate, yes, same rate again. And X1 plus X2 becomes 2X1, which means that X2 has now copied X1. And likewise, it can be the exact opposite. There are 4 reactions here. There are 4 ways that behavioral states can change. Okay. Now, so now we define something called a propensity function. So the basic idea is that of propensity function arises from the idea of the principle of mass action, which you may have learned in chemical some course on chemistry. If you have done any courses that uses chemical reactions, I'm pretty sure it was there in physical chemistry at some stage, even in probably in high school. It's exactly that, exactly that idea. So now let's try to write down. Okay, now there are 4 reactions here, right? Okay. So how can we write down the propensity function? The basic idea is what is the probability that these reactions are happening? That's precisely what the propensity function are. So what is the probability that this reaction will happen? So for example, this spontaneous change in the decision of individual will happen more if there are more individuals in state 1, right? So what does this actually mean? By the way, this equation means that an individual in state 1 is turning to state 2. Now, if there are more in state 1, this will happen more frequently. Okay, so basically the propensity function for this is basically S times x1, where x1 is a proportion of individuals in state. in state. Okay, is this clear to everyone? Just make sure you understand. Sorry. Is this clear? The idea of propensity function for this simple reaction. So if we now understand this, now it should be very obvious what should be the propensity function for this. The more the number in state 2, more frequently this reaction will happen. So therefore, this is just S times x2. By the way, one can think of a more general model where it's for S1, S2, C1, C2. Okay. Okay. So these are the propensity function for these 2 behavioral reactions that are happening. Okay. Now, if you have no, I'll wait for a few seconds to make sure everybody is fine. If you have no questions, I will go to this reaction. Is everyone fine? Okay, I take it as an S. Okay, now what is the chance of this reaction happening? Okay, this reaction will happen more and more if there are more and more in state 1 and as well as in state 2, right? If the numbers go down in any of them, then the chances of this reaction happening is smaller. If the numbers go up in any of them, then chances are actually higher. So the propensity for this reaction will be Cx1, x2. So basically a product will ensure that, take the extreme example when there is nobody in the state x2, this reaction cannot happen anymore. Therefore it has to be a product. Okay. Now what will it be for this reaction? The last reaction, like in be Cx1, x2. So basically the idea is you have to look at the left-hand side of the reaction. Okay, and then basically take the concentrations and multiply them. That's all. Okay, it's a standard thing we would have learned in the chemistry at some stage, physical chemistry. Okay. Now here is the thing. Now the propensity. So I'll wait for a few seconds to make sure propensity function is clear to everyone. Any questions? Please feel free to ask. I don't have no idea, but I can't say you whether what I made sense. What I said made sense.
Sir, so terms like S and C are analogous to the rate constant, and terms like x1 and x2 are analogous to concentrations, right?
What is F and G here, by the way?
S and C, sir.
S and C. S and C are the rates.
Yeah, so they are analogous to the rate constant from law of mass action.
True. Yeah, absolutely. Yes, yes. Those are the rate constants. And x1, x2 are the concentrations. Exactly, yes. It's the same principle, same method actually. In fact, this method was developed in the context of chemical reaction. That's why it's called Gilles-Pease chemical Langevin method. Right. So feel free to ask any such questions. Okay. Any other questions? Okay, so the next thing we do is something called a state change matrix. Okay, so let me write down the state change matrix. Technically, you don't need the full matrix for this case. That's denoted. It's also called some stoichiometry. So the idea of state change matrix, you decide whether you are focusing on the state 1 or state 2. Okay, that you decide. Let's say I'm doing it for state 1, so I'll write a new one. You can write something exactly similar for new 2. Those two then becomes two different vectors. Okay. So let me just write one vector because other one is very easy to compute once you know this. So what this state change tells you, in the state 1, there are two states here, right? There's a binary choice model. Choice 1, choice 2. How does the number of individuals in the state change when the reaction happens? Okay, so let me explain that by this. In this case, and when an individual in state 1 turns to state 2, basically changes the choice, what happens to the number of individuals in state 1? The numbers will reduce, right? So therefore, the state change vector will have -1 because when this reaction happened, the state 1 lost one individual. On the other hand, when this reaction happened, the state 1 gained one individual. Okay. Any questions on what is state change vector? Okay, someone tell me what should be the state change for this?
1.
It will be 1 because x1, x2 became 2x1. So state 1 gained. It will be 1. What about this? What about this? I know it's obvious, but please do tell.
-1.
-1, right? Because state 1 now lost because x1 plus x2 became 2x2. So one lost an individual. So this is the state change vector, and you can write correspondingly new 2, which will be exactly opposite of this. Anyway, two-state model, right? It's actually easy. When the number of states increase, the method becomes a bit harder to implement. So any questions? We have learned propensity function, we have learned state change vectors. Okay, so now here is the basic idea of constructing chemical Langerhans equations. Okay. So Langerhans equation is a general term for stochastic differential equations. Okay. So now here is the basic idea. Imagine there is there are many reactions from 1 to n. Okay, let's say I'm focusing on jth reaction. Okay, now if I focus on jth reaction, and then if I focus on ith state, okay, now because the jth reaction happened, okay, what is the propensity of this reaction? It is Aj. This Aj will depend on whatever x1, x2, x3, x4, all those things. Okay, it can depend on a lot of basically all the concentration. So the propensity of this reaction is Aj. Let us denote this by Aj. This is the propensity function, and that reaction either increases the numbers in ith state or decreases the number in ith state. So that we denote by nu ji. So it's a matrix. So I just wrote one column here, but technically it's a matrix, right? So jth reaction, what is the effect of jth reaction on the ith state? Okay, so when this happens, the product of this will give me change in number of individuals. Actually, it's rate of change, sorry. Rate of change in number of individuals in state I. due to reaction J. Is that clear? So reaction J has happened. Because of reaction J, if I multiply it with new Ji, then I will know how many, what was the number of individuals that got changed because of reaction J. This product will tell me that. Okay. Of course, there are many reactions, right? And there are many types of states. You can have one. So in the simple example, we had only two states, but you can think of it in a more general way. So you can write now the very general equation. The rate of change of concentration of the ith state depend on, okay, there are many reactions J, and each reaction J causes some change in I. So this depends, it doesn't have to depend on, when I say Xi, I mean the entire Xi set. Okay, so this is basically telling when the Jth reaction happened, what was the rate of change that happened in ith state. Of course, there are many reactions possible. Let's say there are n reactions or R reactions. So all of the reactions will cause some change to I, and that is what this is. Is that fine with everyone? Do you agree with this? Okay, let us now apply. If you're not sure, let us apply this in the context of our binary choice model. If I apply this, what will I get by dx1 by dt? Dx1 by dt will be, so what is this new Ji? So, J could be 1 or 2, right? Now, there are actually 4 reactions here. There are 4 reactions. Each of them has some propensity function, and it will cause some change in the state 1. Okay. So, for example, now what all that I have to do is the following. So, dx1 by dt will be product of these two. So, minus sx1, product of these two. So, new times propensity function, right? That will be plus sx2. And then this plus cx1, x2, product of these two, minus cx1, x2. This implies that dx1 by dt is equal to minus s of x1 minus x2. Because these two just cancel out. Do you remember when you did the mean field approximation, we got exactly this? So we're not doing bad, huh? Mean field approximation. And you can also apply this to x2, by the way. So dx2 by dt. You can apply the same principle. So the propensity reactions are all written down. Now, the only challenge is now you need to construct new 2. Okay. So what will be new 2? Let me just write that. Changes into. So, this will cause increase. So basically, it will be opposite, right? So gain in 1 has to come from the loss in the 2. So I can actually just look at the summation of this 2 has to be 0 in this specific case. Loss here has to be gain here has to be a loss here. Okay. Okay, so because those are the only 2 states possible. So now again, I can write down the equation. I don't have to, I don't think I need to, just, do it. I think what you will get is this. Again, exactly same as what we found. Okay. So is this part clear so far? Any questions?
Is this approach a very rigorous way to arrive at the master equation?
This is a master equation in the sense that, you're writing an equation for the state variable x. It is a master equation. Right. Oh, it is very rigorous. Is that what you asked?
Yes, sir.
I have not answered the question. I think whether it's very rigorous or not depends on whether you're a mathematician or not. So. It's reasonably rigorous, yes. So you can read the original paper to understand. Okay. So far, any other questions? That's a good question, very good question. Any other questions?
So I was just thinking about applications for multiple state variables. Is that possible in this framework?
Can you repeat your
So,
question?
so if you have, say, two state variables, right, X and Y,
Yeah.
can this sort of framework be applied to that situation as well?
Yes, yes, right. We already have X1, X2 here. Right? There are two state variables, 1 and 2.
No, those are two possible states, right? I'm talking about, like, say, if you're applying this to an ecological system with consumer and resource.
Predators and prey.
Yeah, something like that. Yeah.
Absolutely, yes. Possible. Yes.
But then you would have to code it differently a little bit.
So the only difference there, here, see, what will change. So for example, this could have been technically predator, prey, prey becomes predator. Of course, doesn't make sense. I fully understand. Okay. But, you can write down this kind of how the interaction between predator, prey are happening via chemical reaction. This is called a chemical reaction sort of, notation of how the interactions are happening. So it is possible to write down a lot of basic ecological interactions in this format. Not all, but many of them. It is possible. Okay. And then you find the propensity functions, and then what will change is basically this. So here there was a constraint, right? A loss in one had to mean a gain in the other one. That's not always true. For example, think of contact process, the population model, right? There the death doesn't necessarily mean another birth somewhere, right? So these two need not add to 1 in that case, 0 in that case. So yeah, it's possible.
Right. Okay.
Okay. So now here is the thing. What if we set out to do, by the way? We set out to write down the Langevin equation, which actually captures the stochasticity. Have we done that? We haven't done that. What we have written down is actually a mean field approximation. It's just another way, or maybe even an easier way of arriving at the mean field approximation, right? So in fact, without knowing chemical Langevin equation, you all derived the mean field equations for X1 and X2 for this model, right? So far, we actually haven't done anything new. We have just writing it in a new way. Okay. So now, what is the stochastic part here? So that requires me to say a few things. Okay. Which is as follows. So there is a very interesting way to arrive at the stochastic part. Now let's look at the following. For this, I need to revise a little bit of probability for you. Now, let us say if I tell you that an equation like this is happening at some rate is, what does it actually mean? Okay, so what it actually means is the following. Let's say there are, if you are in state 1, okay. For example, state 1 could mean I'm moving towards right side. Okay, so in the context of animal movement. Okay, state 2 could mean I'm moving towards left. Okay, so when will I switch my direction of motion? That's what this equation in that case means. So what does this mean? X1 becomes X2 at some rate. What does it actually mean? What it actually means is the following. At a time, let's say at t is equal to 0, what it means is that this individual will draw at a random number from exponential distribution with mean 1 over s. Okay, so you draw a random number from an exponential distribution with a mean 1 over s. Let's say that will give you some number. It's called the tau 1. What do I do to that number? What this means is that I will switch from x1 to x2, switch to state 2 after tau1 time. Okay, that's what this actually means. You have to understand the basic way of probabilities. Yeah, go ahead.
Right. So is there a reason why we're using the exponential distribution?
So basically, whenever we say rate, something happens at a rate, it's always exponential. That's by definition.
Okay. All right.
It's a definition. Okay. And there is a good reason why mathematicians use it. It has some very interesting property called memoryless property, which I won't get into here. And that's the reason all these reactions are used in this context. Okay. And now, of course, you have actually come across this. Okay. Where have you come across it? I'm sure in your high school again, at some stage, or even in your MSc, BSc courses, you would have come across two instances. Okay, one is a radioactive decay. Okay, the other one is that of what is it called? The population growth or population decay. Okay, all of them. So whenever any, basically, actually, let me just I think I made a wrong statement just a while ago. Any activity, any event that happens at a constant rate, implies that the wait time for a specific event to happen is exponential. So it's actually a mathematical equivalence here. It's not really an assumption anymore, actually. Yeah, at least mathematically, when you say that certain event is happening at a constant rate, that is same as saying the wait time for that event is exponential. Okay. For example, if you go in a bus stop and say that, oh, the bus arrives here at a rate of 1 bus per 5 minutes, it doesn't mean that at every 5 minutes there is a bus. It actually means that the wait time for me to find the bus is follows an exponential distribution. Okay, with the mean value given by that. Okay. So it's it's a very useful mathematical statement that's sort of incorporated in all of these scenarios. I think it comes. Was another example which I should have just remembered in biology, which I immediately. I mean, some of you might know better. Where all have you seen exponential wait times? Exponential. Okay, so this is the first information I told you. When something happens at a rate s, it means that your wait time for that event to happen is 1 over s. Mean wait time is 1 over s, but the actual wait time is a exponential distribution. Okay, is it clear to everyone now? That's the first fact you should know. Okay, this is the first point I want about this. The second point to make is the following. The second point is as follows, which is if I, for the same reaction, any reaction that happens at rate s, if we wait t time units, number of events follows what distribution? So here is the scenario I have just told you, right? Imagine a scenario where you're waiting at a bus stop, right? And let's say the bus arrives at rate s. That means that the mean wait time is 1 over s. It means that the actual wait time is an exponential distribution. That part we understand. Okay. Now let's ask a slightly different question. For the same rate, if the bus is arriving at a rate s, if an event is happening at rate s, If I now wait for t time units, how many events do I expect to happen? How many buses do I expect to arrive in that time t units? Okay, that's the next question I'm asking. This follows Poisson distribution. Okay, Poisson distribution, and if I'm okay, and you know, both exponential distribution and Poisson distribution have the following property, which is that the mean is equal to variance. Did all of you know this? Any question on this? Okay. Okay, I might take it as an S. Okay, now armed with these two informations, okay, we need a third information. Okay, I'll tell you what it is. Under some considerations, Poisson becomes normal distribution. So I want to distinguish fact 1 and fact 2 from fact 3. Fact 1 and fact 2 are mathematical certainties. Okay, fact 3 is an approximation that is true under some circumstances. Okay, when the mean is high, when when the mean of the Poisson distribution is high, then this approximation is a good approximation. Okay, so that's where we are. Now let me go back and apply all of this in the context of our equation. Let's go back to our equation now. Remember, we had propensity functions. We were thinking of how numbers are changing. Okay, now let us consider a time unit delta t. Okay, now what will be the change in the number of concentration, or the number? Okay, the concentration of, technically I should be rewriting this in the numbers and then do some mathematical transformation. That derivation, I can just give you a reference, but I'm just going to use heuristics right here. Okay, so we are now trying to see what happens in a time unit of delta t around t. Okay, so as I already told you, which is basically a discretized version of this, by the way, discretized version of this. So we're looking at what happens in this time, time interval delta t. So we know that the rate is given by this. For each reaction, the rate is given by, rate of event is given by nu ji times aj. Okay, so xi changes because at a rate nu ji times aj for each reaction j, right? So basically nu ji aj, that depends on x, and if you multiply the rate with the amount of time that is taken, that gives you an average change, or the mean change that's going to happen in time delta t. Okay. Okay, but remember, if we have a let's use these two facts now. So if an event is happening at rate s, okay, then if I wait for t time units, the number of events follows the Poisson distribution, right? With the same rate, by the way. So the same rate is happening, but there is also a variation around it. Let's write the variation around it. So the variation around it will be such that the mean is equal to variance, meaning the standard deviation will be square root of the, okay, mean. So if you do the mathematics carefully, this is what you will actually find. Okay. Let me just write down and then justify. 1 over root n mu ji, again the same mu ji, aj, the same reaction aj, with the square root and with the Gaussian random noise. Okay. And of course with the delta t again. Okay. Actually root delta t, to be very precise. Okay. let me try to explain. This is, crude. Let me just state without any hesitation. I have written this crudely. Let me try to see if I can make sense out of it. Okay. So imagine that there was only one reaction that was happening. Okay. If you wait for delta t time. Okay. So what is the expected change in a mean sense? That will be just the rate times the time interval. So that will be the expected change in a average expected change. But we do know that there is variation around it. We do know that this variation follows a Poisson distribution, and in some limits that Poisson distribution can be done as normal distribution. So what I have done here is that for each of the reactions, we have taken a square root to get the standard deviation, and we're multiplying with the state change variable. And then instead of Poisson distribution, we are saying that, well, let us write a normal distribution, because under some limits, it's actually a good approximation. Okay, so it's a basic idea. So the mean average change comes from this idea that from the rates, mean just like the mean field approximation, and the variance around it comes from this Poisson distribution, normal distribution equivalence. Okay, so that's how these two terms are derived. Now we can now go back to the differential equation form and say dx by I by dt is, this is the mean field term basically for all reactions, and then this is the stochastic term. Okay, this is called the chemical Lanzarine equation. So what is nice about this is once you know the propensity function, you can actually write down the chemical Lanzarine equation. So any questions? So of course, if you want a more rigorous mathematical proof, I will give you the reference, which you should be welcome to read. Is it fine? Any questions? Okay, so now that we have done this, let us apply this, right? To see if we really understand, and let's see what we find for the simple binary choice model. So the binary choice model, we already know what this gives us. This gave us just a very simple equation, right? So which is dx1 by dt was minus s x1 minus x2.
Sorry, Vishu, I just had one doubt.
Sure.
What is n in the above equation?
That's the whole point. N is the population size. Okay.
Population.
So if we had an infinitely large population, or a very large population, you can ignore this, and therefore chemical Lanzarine equation basically becomes mean field approximation. That makes sense, no? When you have a very, very large population size.
Right. Yeah, that makes sense.
The noise is irrelevant to the average. Okay, thank you. And eta j is a Gaussian white noise that we have used in the past. Okay, so okay, any other questions, please? Okay. Okay, now let us look at this. Okay, the stochastic term. So, so there are, this has to be, now there are 4 equations again in our case, right? Let's go one by one and see what do we have. The first equation, the propensity function is Sx1. Okay, and then the state change is -1. The first term will be, okay, here is a simple question I have. Does the sign of nu matter at all? Okay, let's say sign, we know that in our case, sign of nu is either +1 or -1. Okay, it's nothing else, right? So let's consider minus eta and plus eta. Both of them are Gaussian random, where eta is a Gaussian random number. Is plus eta and minus eta in terms of distribution, are they different? Are the same? Aren't the same? Because eta is anyway a Gaussian random number, which can give you either positive values or negative values. Whether you put a minus sign or not is totally irrelevant, because on an average, you will still get the same set of numbers, right? So it really doesn't matter what exactly the sign is. I'm going to ignore the sign when I'm going to write, I'm going to ignore the sign entirely when we write this equation, okay? So for the first equation, we have, okay, let me just write anyway for the sake of completeness. I'll say -1, that's the nu, and then we have aj, which is square root of sx1 and n1 of t. This is a Gaussian random variable, the first Gaussian random variable, okay? Now just look at the second and third terms. They're both positive. The next propensity function is sx2 and then cx1, x2, okay? +1 square root of sx1 minus, again another plus, square root of cx1, x2 this time. Okay, and then again we have a minus sign, the last one. We have minus sign and with this square root of cx1, x2. Data 4 of t. That completes all the stochastic terms. Any questions in this? Basically applied this chemical Langevin equation to the binary choice model. Is that fine, everyone? Okay. See, what was the difference between the mean field term and the stochastic term is as follows. In the mean field term, we had exactly same terms. So look at this, the summation of nu j I aj. We again have summation of nu j I aj, except that the aj comes with the square root term. Okay. That is because the mean and the variance are same. So variance will be basically aj square. Whatever the term here is the square, right? So that's why we have a square root term. And because each term is multiplied with a different type of noise, they're all different noises. Eta 1, eta 2, eta 3, eta 4, they're all Gaussian white noise. But at a given point of time, they may shoot different random numbers at you, right? So therefore, I cannot cancel these two terms. Okay, it has to be next to here, sorry. These two won't get cancelled anyway. So these two basically got cancelled deterministic term, but they won't cancel here because the eta 3, eta 4, they might actually give you different random numbers at each instant. Therefore, I cannot cancel them out. Okay. So therefore, this term is now a longer term compared to this, the stochastic term. Okay, anyone, any questions, people, on this?
So the noise is sampled differently for each reaction. It's
the same distribution, except that they are different random numbers. Let's say if both of us simultaneously drew a random number from Gaussian distribution, we won't get the same number, right?
Right, yeah.
That's what is happening here. Yeah. That's why we cannot cancel those terms out. Okay. Okay. Now let us try to simplify this a bit. Now, to simplify this, you need to know a little bit about some property of random numbers. Imagine there are two random numbers, eta 1 plus eta 2. If I just add them, which are, then basically you can replace it with a new random, imagine that they have, let's say they both have, so eta 1, eta 2 have, just variance 1, okay, mean 0 and variance 1, okay. Then let me just say that. Okay. Let's say that there are, let's say that the mean of eta 1 is 0 and the variance of eta 1 is 1. If, and then let's say same is true for eta 2. Okay. Now let us consider the following: sigma 1 eta 1 plus sigma 2 eta 2. This is also a random number, right? It's just a combination of two random numbers with coefficients. So this has the, let's call this eta. So it turns out that the mean of this is basically mean of the entire right hand side. That will be basically sigma 1 mean of eta 1 plus sigma 2 mean of eta 2. Since both of these two are 0, this is still 0. So the mean of the summation of two random numbers is same as the is basically 0. How about the variance of this? Now for this you need to know a little bit about, this requires a longer calculation. It turns out that the variance of this is nothing but sigma 1 square plus sigma 2 square. Okay, this of course I'm not proving right now, it requires a few additional steps. Assuming that eta 1 and eta are independent. If they were not independent, you will have an additional covariance term. So this is what happens. Okay. Now this can be generalized to as many terms. If there were sigma 3, sigma 4, then it will become sigma 1 square. Okay, so what this basically means is that if there is a linear combination of two Gaussian random numbers, I can replace it with another Gaussian random variable with, which has the corresponding mean and the variance. Is that clear? So instead of doing this, I can just take an eta which has these two properties. That will be same as drawing two random numbers independently and multiplying them and then adding them up. Is everyone okay with this? Okay, if it is okay with this, now we can simplify this entire term. This entire term now can be simplified in the following way. What will that become? So we basically take square of all the coefficients, add them up, and then replace this with another with a Gaussian random variable. So basically all of that will be Sx1 plus Sx2 plus 2C x1 x2. Of course, what we want is a standard deviation times. Is it fine? Basically, I have taken the square of this, square of this, square of this, square of this, and add them all up, and then I have replaced with a single random variable. Okay, so therefore dx1 by dt is given by minus s x1 minus x2, which is the mean field term, plus is the stochastic term. Except that I forgot one key term. This entire thing gets multiplied by 1 over root n. So this will be 1 over root of n. Any questions? Where n is the number of individuals in state 1 plus state 2 put together. Any questions? Okay, if there are no questions, now can we write down a similar equation for Sx2, by the way? So, because the reactions are so symmetric, I can just look at this and just swap x1 and x2 with the correct equation, right? S, x1, S. So as you can see, if I swap x1, x2 here, the entire equation doesn't even change. Is that fine?
Shouldn't the deterministic term be x2 minus x1?
Oh, you're right. Thank you for that. Yes, you're right. Okay, yeah. Now, except that I made a small mistake here. If this is eta, I should call this maybe eta whatever, eta prime. Okay. So these two noises are not same. So noise acting on x1 and x2, they're different noises. Okay. Now we are interested in, remember in this problem of binary choice, we are interested in a quantity called m, which is x1 minus x2, which tells you it's a consensus parameter. If everybody was in choice 1, this will be 1 minus 0, this will be 1. If everybody had chosen choice 2, it is 0 minus 1, it will be minus 1. So basically, both m is equal to plus 1 and minus 1 indicates consensus, that everybody is doing the same thing. It could be moving in the same direction, it could be choice of nest site, choice of food, and so on and so forth, right? Whereas m is equal to 0 means that they're split evenly between two choices. Okay, so this is the consensus parameter we are interested in. Okay, so now how do we obtain this? What all that we have to do is now basically subtract the two equations. Okay, if I subtract, the left hand side will become d by dt of x1 minus x2. That will be now subtract deterministic terms. So now we will have 2. Okay, these two will actually add up when you subtract them. If you subtract these two, what happens? You have this stochastic term minus this stochastic term. It's a subtraction of two stochastic terms, or the addition of two stochastic terms. Okay, again use the same principle now. If you take addition or subtraction of two, this addition or subtraction, why am I saying it so? Because the coefficient can be positive or negative. The eventual outcome anyway depends on sigma square, right? It doesn't really matter whether subtracting or adding. So now if I subtract these two, basically the effective noise will be square of this added to the square of this, and with a new noise. Okay, so I'm doing that. Okay, so these two terms are same. So what I will basically have is 2 by square root of n times sx1 plus sx2 plus 2cx1 x2. And let's call the psi now, psi of t, where again this is Gaussian white noise. Okay. Is everyone fine so far? What is this, by the way? This is n. So this is dm by dt left hand side. What is this? This is minus 2sm. Okay. And then this is 2 over square root of n. By the way, I have been very stupid all along. What is, if I take s common factor, what is x1 plus x2? It's a proportion in state 1 plus proportion in state 2. What should that be? It is always 1, right? So this is basically this entire term is basically equal to s. So s plus 2c. Okay, now what is x1, x2 in terms of m? Okay, so now as you know, m is equal to x1 minus x2. You also know that 1 is equal to x1 plus x2. If I multiply these two equations, what do I get? I get, oh, no, I shouldn't multiply. No, what should I do? No. How do I get the value of x? Okay, I think maybe let us square this. So I'll get that x1 plus square plus x2 square plus 2x1 x2 is equal to 1. Let me also square this. I'll get x1 square plus x2 square minus 2x1 x2 is equal to m square. Now let us subtract the two equations. Then I will have 4x1 x2 is equal to 1 minus m square. So what I have is 2c x1 x2. That means 2c x1 x2 is equal to 1 over. I have taken 2, but I have multiplied by 2. No? So c by 2 times 1 minus m square. Is it correct? Did I make a mistake or is it fine? So basically 2c x1 x2 can be substituted by c by 2. Okay, is anyway, okay, so this is c by 2 times 1 minus m square times psi t. So we have now derived actually a stochastic differential equation. This is a stochastic mean field approximation for the binary choice model. This is not just a mean field approximation anymore, but it actually has a stochastic mean field approximation. Is everyone fine with this? Is it too much for one day? Please ask me questions.
So are eta t and eta prime t distributed differently, or are they?
So they're all, see, I think is no, I have used a property of the Gaussian random variable in this step. If you take a Gaussian random variable, if you add them, you will get a new Gaussian random variable with different mean and different variance. That's the basic principle I have used. But it still remains Gaussian. Whenever you add two Gaussian random variables, it continues to remain Gaussian random variable, except the mean and the variance may change. But luckily in our case, since all the means are 0 throughout, the mean is not changing. Only variance is changing. Is that clear now? So basically all of them have same distribution. In fact, all of these that I'm writing have, all of them have mean 0 and variance 1. All of them. Because effectively I am dealing variance in an external way as coefficients in every one of the case. And I have used this formula repeatedly. Variance is this. For example, when I'm subtracting this from this, right? Now I'm subtracting a Gaussian random variable with some coefficient with another Gaussian random variable with another coefficient. Okay. Now you can think of this entire thing as sigma 1, this entire thing as sigma 2. Okay. So just like sigma 1 eta 1 plus sigma 2 eta 2 can be replaced by another eta, but with a different sigma. That's precisely what I have done when I come from this to this. And I'm subtracting.
Yeah.
So
Okay.
steps.
Thanks.
Any other questions? I hope I didn't make any other algebra mistake. Huh? Is it fun? It's possible. Okay. What one can technically do is to divide the entire thing by 2 and then change the time scale. But I won't do that. Okay. But anyway, so what is interesting? There are two interesting things that I want to point out here. If you go back to the binary choice model, there were two parameters, right? Oh gosh, they become so tiny now. Spontaneous reaction and the copying reaction, pairwise copying reaction. Okay. What is very interesting is that if you now come back to the final equation, we always, the mean field term depends only on the spontaneous reaction, not at all on the copying reaction. Whereas the stochastic term depends on both spontaneous reaction term as well as the copying reaction. So, copying did not make any difference to, the mean field term at all. Okay, but it did make a difference to the noise term, stochasticity term. What this means is that when the copying is more, stochasticity is actually more, right? When if we increase C, right? If we increase C, this strength of noise actually increases. So it's also very interesting with a multiplicative noise. M is a multiplicative noise, right? M is a state variable, right? The strength of the noise depends on the state of the variable. What this also shows is that ad hoc and introduction of noise. So imagine that if I had asked you, if let's say if we went back here, right? If we went back, we derived the mean field model, which would look like this, right? Okay. If I had now asked, okay, can you introduce some noise here? How will you introduce noise? If I had asked you how will you introduce noise, you would have just introduced a noise in an additive way as the most simplest way. That doesn't capture the state dependent part at all. Alternatively, you could have said, it's a parametric noise, S is stochastic. That still would not have captured the nature of the, this full nature that we are discovering here. So what the sorry. So what the chemical Langevin equation approaches allows you to actually construct the stochastic term in terms of the behavioral rules or the interactions in the, among the organisms. Sorry. Okay, fine. So I will stop here today. I think it's very intense class. Make sure you revise what I have done. We will continue on Monday. Is that fine? I'm also very tired because I have very heavy meetings this morning and I'm getting cough. So we won't have any lab work. Please, try to do on your own. Maybe apply this method to ternary interactions and so on. Maybe I can give you one very short assignment equal to lab assignment that you can submit by Monday. Okay. That way, the thing is, I don't want to give a fourth assignment, which is very heavy, become very heavy given that. Maybe I will do the following. Don't have to do it now in the lab, but still do it in groups. I think what I would like you to do is very simple. I have shown you how to use. Where is the? Oh. So I've shown you how to use chemical Langevin equation for one model, right? I have derived, but I have shown you how to use this. Just apply chemical Langevin equation. You remember we had done another binary choice model, right? I don't know which lab was it. Was it 2 weeks ago? This is something called, this full model where you have stochastic turning, pairwise copying, and ternary copying. This model. Okay. Can you apply that, the chemical Langevin approach and derive the Langevin equation for this ternary complete model? This ternary, which has all the three, all the three stuff. Okay. I think you had derived the mean field equations for it. So actually it's nice because it will be a nice continuation. Okay. From where we left here. So same rules as in class 16L, page 3, but derive. Okay, let me just do it in a new page. Okay, derive for ternary model, which has, all the three reactions, it has spontaneous, pairwise, and ternary. It has all of them with those rates, okay, defined on class 16L, page 3. So that's your lab assignment. Is that fine? I think let's have a lab assignment to make sure that I don't have to give you any more homework. Okay? Whatever number it is today, I don't remember that. Maybe 8, I think. And you can submit by Monday. That's totally fine. I'll set up the, no? Okay. Any questions before we close the class today? I just had a couple of announcements to make. Next Monday, we will have a class. Friday is a holiday, I think Guru Nanak Jayanti. And that leaves us with basically another Monday and Friday. Okay. So we basically have 2 Mondays and 1 Friday. And please be ready in principle for your. So did I already announce the date for the presentations or not? I have already forgotten what I did. No response. Okay, I think I haven't. So I will announce it on Monday. Okay. So please be around. Monday we will decide the dates for the final presentations, for project presentations. Okay, that's it from my side.
Sir, in the dx1 by dt equation, if we add the 2 differential equations, will we get a new relation?
How? Tell me what happens if we add 2 equations? Intuitively, what will the left-hand side be? D by dt of x1 plus x2, no? What is x1 plus x2?
It's a constant.
It's 1. So what will the left-hand side be?
0.
0, right? So what will the right-hand side? These two will also cancel. But what happens to these two now? They won't get cancelled, right? So that's always the tricky part with stochasticity. Why do they not cancel? Right? So they don't. Is it your question, by the way? Why does it cancel?
Yes, sir. I thought that maybe there will be a relation between the two.
That's a good point. So basically, for this to cancel, the noise have to be sort of also same. Is that what it means? They're actually same noise. It's a good point. I will think about this. Okay. I thought the noise sources were independent. Yeah, that's a good point. I don't know. Okay. I mean, I can give a lazy answer, which is that, both equations are technically approximations, right? Where does approximation come in the fact that we said Poisson is Gaussian, right? That's one approximation, right? And that, yeah, maybe I wonder if that is the one that causes, but still no, it must be a identity sort of thing, right? It must cancel. Why doesn't it cancel? I will think about this. If you have an answer, let me know. Okay. Any other question? It's a good question because I don't know the answer. Okay, cool. I'll stop here. I'll set up the lab assignment on the website and then we'll set up